All right. Hello and welcome to topic 2A of our Introduction to Statistics course, where we are going to move on to our next topic and try and understand some concepts. In this case, the title is Central Tendency and Variability. What all those words mean, we will get to soon enough. Don't worry about it. So, um, let's remember the importance of what we call descriptive statistics. We have some data we want to describe, hence the name, describe what we see, what properties these set of scores have. And down the line, we want to use that in some way to make sound decisions for future. But right now, we just focused in topic 1 on describing it. And we use the frequency table, we use the histogram, bar graph, depending on the type of variable. But more than that, we want to summarize the data by way of one, two numbers. And that can be used to describe the data as well. We want to summarize the distribution of the scores that we have. We want to do that as a single number. It's perfectly fine to look at the histogram and describe it in words, but we can't use those words in a future calculation. Having a single number that we call a measure to describe what we see in words can be, and turns out is, very useful. Now, when we look at distributions and the histogram and scores that we might collect, there are two properties, really. Two main properties that we want to capture and say something about. We have the position. I'll put this in quotation marks. The position. And we have how the scores are spread out. The position and the spread. So when it comes to the position, where is it located? Where is the center? Where is the peak? Just where it is. If I talk about the height of people, then is the height, and I want to represent the height with a single number, is the height around 6 feet? Is it around 4 feet? Where is it? So we have the need for a measure of sort of position or center. Say what we mean by that first. Then also, if I look at the height of people, I've measured some people, I have my scores, and I know it's sort of positioned around 5 feet. Are they all very close to 5 feet? Or does it vary wildly from 6, 7 feet to 4 feet, all over the place? The spread of how the scores are spread around isn't captured by the position. It's a separate, somewhat independent property. and we'll call that the measure, or it gives rise to the measure of variability. Spread, right? So first up, let's put first here, we want to see how can we measure this concept of center or position. Let's put a squiggly line under it. Well, first up, we could just take the scores and average them. Of course, I'm talking about numerical variables here so that I can actually perform a calculation on the scores, and we're going to call that the mean. But it's just the average that we all, I think, know. Most commonly used, most common for numeric variables. That was supposed to be an RI. There we go. I just take all the scores, I sum them, which means I add them all up, sum of the scores, and then I divide that sum by the number of scores that I used. If I start building slowly a formula sheet, this is the formula sheet that I am going to use. It's in the first pages of the Statistics for Psychology book, Formula 2.1. Let's just copy that down and talk about what the symbols mean. Get it? Mean. What the symbols represent. So that Formula 2.1, and it is the mean, which will represent by the letter M. Have this capital sigma. Mine looks a little curvy. Let's make it Greek-like, which is our symbol to say we're adding up all the X scores divided by how many there are. So N in one form or another will be used to represent how many scores there are. This capital sigma, the Greek letter, indicates sum, that I'm adding up all the scores corresponding to my variable X that I have, and M will be the mean, the answer. All right. So I want to get used to reading these formulas. They are in a sort of condensed form, but it still gets the point across for how to do this calculation. I don't have to remember it necessarily. Let's have a little look-see. Calculating the mean. Hide some of it first. Just double check if this is all on my screen. Yeah, it looks good. The random line. So let's look at an example where people's stress ratings were collected. They were asked uh, some questions and on stress, and they got a stress rating. If I add all these up, I get an answer of 193. Now, of course, remember, we are actually going to do this by hand and so on in our part B of this topic. Right now, it's sort of done for me on this. I count how many there are. There are 30 of them. So the mean, here's my formula. Adding them up, the sum is 193 divided by 30. I get a mean of 6.43. If I look at the distribution, the histogram, the mean sits over here. I can sort of see that as a balance point, like the average. The average, sort of a balance point. It gives me a single number to represent the center of this distribution. Some are on the left, some are on the right. My distribution is positioned at 6.43. So when I talk about the measure of center, I'm not saying anything about how it's spread around this mean, that is a completely separate issue. Just where is this located? Well, the average stress rating scores 6.43. And that then tells me, okay, it's not low stress, it's not super high stress, but it is on a little higher than stress rating scale. That gives me then information by just a single number. Good. So the mean is the first of these. Another one is the mode. That is definitely important to keep in mind when I'm trying to describe a distribution. Did I underline mean? Did not. Ah. It is very simple. It is the score that occurs most often. Occurs most often. So I could just look in my frequency table, and find which score occurs most often. And this is more useful for categorical variables where I can perform a calculation on them, right? There is no average of categories. Categorical variables where I want to say, oh, this category occurred most often. Let's have, we're not going to have, apparently I don't. I thought I had a graph on that, but I don't. It's so simple. Apparently it doesn't need a graph. Let's move on. So the mode, by far, I will admit, the mean is the one that's going to dominate our discussion moving forward, but I want to be aware that there are others. Mode is one of them. That's not necessarily captured by the mean, right? Here, the mean is 6.43. The highest, the score that occurs most often is 7. So yes, it's close, but it's not exactly the same. Look at another example where we want to go back to the mean, more important, especially when it comes to numerical variables, or numeric variables. Let's look at this horn honking example, which you may remember. Very interesting that we measured how long it takes for people to get on the horn when the light turns green and no one in front of them is moving. So we got these 29 numbers, scores rather. We calculate the mean as 2.84. So the average time that people took is 2.84. Note that that's not one of the scores, right? It's somehow a merged version of these scores to represent all of these scores, all of these numbers by a single number, single measure. To give me an indication, uh, on average, this collection, does it sit high? Does it sit low? Well, it's kind of in the middle. Kind of in the middle. So the mode here, I do have an example, sort of. If I look at my frequency table, the mode is the score that occurs most often. The most often, the score of 3.5, it occurred 6 times. So for somewhat balanced distributions, the mode and the mean is going to be fairly close. If it has some sort of peak in the center, tapering off to either side, like close to normal. But these won't necessarily be the same. Just note the mode isn't 6. The mode is the score that occurs most often. The score in this case is 3.5. All right. So different things depending on what I want to reference, what properties I want to reference. But they're both kind of an indication of where is this distribution positioned. All right, now there is a little bit of a problem. Problem with the mean. It's not a huge problem, but it is a problem. That, excuse me, let's look at an example. Go back to the horn honking example. Initially, so this, let me make my cursor way less, maybe a 3. Initially, we had these 29 scores. They're arranged here, doesn't matter right now. And we got a mean of 2.84. Great, good, 2.84, somewhere over here. However, let's suppose there was one more case. We measured one more person, a very patient person that took 13 seconds before they honked the person in front. Now we have 30 scores. We calculate the mean, adding up all of these, dividing by 30, of course, and we get 3.81. The presence of this extreme score relative to the others, we'll call it an outlier. It's much higher than anything else, right? In the calculation of this mean, this average, it pulls the answer, it pulls this mean towards it in a much more drastic way. So we want to say, well, okay, it doesn't seem like a lot, but relatively speaking, it's much bigger than 2.84. Does this 3.18 really represent this whole group of scores? Well, no, not really, as much as it did previously. The presence of this outlier really pulled the calculation towards it when it kind of shouldn't, right? So if I go back here, the problem with the mean, whoops, my cursor is very light now, let's go to 10, is it's very sensitive to outliers. Those outliers in the calculation will pull it towards them when they kind of shouldn't. They're one, they're one score among many. It shouldn't have that big a role in determining this mean, this single measure. It's one of many. It should have the same role. But unfortunately, the way the mean is calculated, it does not have the same role. It has a much bigger effect. So in steps the solution, and it's called the median. Median is useful when I have some outliers. Useful when we have, or even if we suspect, we have a few outliers. Then we know that, yes, we can still calculate the mean, but the answer we get is not going to be the best representation of the distribution of the set of scores as a whole. Now, all the median is, it's the middle score. What do I mean by that? I mean, we are going to arrange, that was ugly, arrange the scores and then simply pick the middle one. And we'll see shortly how does that actually help me. So I think this was our last slide. Let's go to this one. So let's have another, actually, go to the horn honking. I'm looking for my, oh, where am I now? Okay, let's look at this one. I thought I had a slide showing it, but whatever. For these two. They are already arranged for me. Great. There are 29 of them. So halfway would be the 15th one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This cursor is too big. So the median would sit over here. That would be the median. 3. If I have an odd number. If I have an odd number, there is an actual middle score. If I have an even number of scores, like the second line, also arranged for me, the middle two are over here, right? They're both 3. I take the average of them. The median is still 3. So here's the median. You see here that the presence of this outlier didn't affect the median. And even if these two scores weren't the same, they're arranged. So it's going to be the next one up. Not going to move much. So the median, though it could change with the presence of an outlier, it's going to change very slightly, where the mean is going to change much more drastically when it kind of shouldn't. It's built into the calculation, not much I can do. I can look at the median instead and have something that isn't as affected by the presence of outliers. Median. Let's go to this one, just another example of the same thing. Let's suppose I have some scores here coming from whatever. I have a bunch of 1s and 8 and a bunch of 9s. The mean, average, 5.27. The median is the middle one. It's already arranged for me. It's the 8. If I have scores not too far down below 8, but sort of split in two almost. I have a lot of low scores and a lot of high scores, but I have just one more low score. The median is still 8. So the median isn't perfect either. The mean, in most cases, I don't have, so here, no outliers. No outliers. Outlier is just a handful of extreme scores, a handful relative to how many scores I have. Not half of them. Those aren't outliers anymore. These 50s are actually a strong part of what this distribution is about, what scores I could get. An outlier is a score that I can get very rarely. It'll almost never happen. But unfortunately, when I took these measurements, it does happen. These 50s are not outliers. They're quite common scores. Almost half of them are 50s. The median doesn't capture that. It just picks the halfway mark, whatever that may be. And when I have scores that are so sort of divided into low and high, then the median isn't a good representation. The mean is the better of the two. So the median doesn't try and compete and take over as the important measure of center. The mean is the one. But in some rare cases, I should be aware that the mean has its flaws and the median just tries to fill in those little gaps. Okay. All right, let's look at the next slide. Horn honking example again, which I don't think we've done for the median. We've done the mode, then the median. I arrange all these, which can be very tedious to do by hand. We shall see. Look for the middle one. Median is 3. And see, it is, in most cases, when I have nice symmetry, it's not skewed to one side, the median, the mean, the mode, they'll be fairly close to each other. If I calculate the mean, good. Maybe I don't know if there are outliers. I can calculate the median as well, just to confirm that the mean is a good representation when they're close. So just a tip here. If I have an odd number, there is only a single middle. If I have an even number of scores, then there are 2 in the middle, and just take the average of those 2 scores. And that will be the median. Just add them up, divide them by 2. Just those 2 middle scores. Right. Let us move on. There, I can use the mean median mode to confirm, I guess, possible skewness. When I have everything perfectly symmetrical, mean median mode is going to sit right on top of each other. I have the average calculation balances two sides. The middle is exactly the same thing. I only have one peak, which is the mode. Everything's good. But when I have a negative skew, the mode will still be at the peak, right? And the median will be a little to the left of that, and the mean will be a little further left, being pulled by these few extreme values on the left. And in the case of a positive skew, I have it the other way around. So I can look at the positioning of the mode, median, and mean, and when they're sitting in line like that, then that it can indicate skew in that direction as well. So let us move on. Which slide was this? All right, which number was this? So I can just make sure I am track here. That is good for our introduction measure of center. Again, mean, most important one for us, where we will focus largely on numeric variables. Be aware outliers can happen. The median just tries to help us in that regard. Now, let's have a look at this. These few histograms. Let's look at B first, this right side, where the distribution is pretty much the same. Not exactly the same, pretty much the same. Previously, we want the measure of center, the mean, to give me an indication of where does this distribution sit. In this first one, it sits around 1.7, which is very different from a distribution that sits around 3.2 or 2.5, depending on whatever it measures, right? Whatever scores we are working with here. So the mean tells me the position, like we said, quote unquote, or the center. But it doesn't tell me everything about this distribution. Look at this left column, A. In all the cases, I have a mean of 3.2, but these are not the same distributions at all. The bottom one is quite balanced, actually perfectly balanced. The middle one, no, it's sort of skewed, it has negative skew, but it has two peaks, very different. The first one is, I guess, a much more traditional negative skew, one peak sloping down. So how the scores are distributed or spread out around this mean is something that is a key property of the distribution that the mean doesn't capture. But in order for me to effectively describe the distribution of scores, I need the mean and I need a measure of how scores sit around the mean, variability. How much do I expect in this first one? Yeah, there's a little bit of variability around the mean, not much. I go far out, I didn't get anything. In the other two, I can go further out and get more scores. Middle one sort of in a balanced way. I can get more scores going further out, like 2 bars out. In the top one, I get more scores if I go higher, not so much lower. All these are different, yet the means are the same. So we need a measure of variability. Let's make my pen big. We need a number, oops, that's an R, to represent the spread away from the mean, around the mean. So I'll just make some notes here. The measure of center alone doesn't completely describe the distribution. It does describe something, but it doesn't completely describe what is happening. It's only half the picture. My writing is not very neat today. That's okay. So what do? We need a way. Oops, not, I already have the A. Describe this spread around the mean, away from the mean. We can do that by, deviation. That's going to mean? It's simply going to mean, what is that going to imply? That simply is going to be, I take my score and I subtract, so minus the mean. Let's have an example. I don't have a slide for this one. I'm just making it up. Let's say we have the scores 4, 4, 4, 4, and 4. All scores are the same. Then the mean, M, is going to be the average of all of these. I get 1, 2, 3, 4, 5. 4s that I add together is 20 divided by 5. It's going to be 4. Right? Obviously. So that's going to be my first example. If I look at the deviation scores, that's supposed to be a C first, deviation scores. I'm going to take the first score and subtract the mean, 0. Next score, subtract the mean, 0. And so on. They're going to all be 0. So if I add up all the deviation scores that we're going to represent as the sum, the x is the scores minus the mean, add all of these together, I'm going to get a 0, which makes total sense because there is no deviation. There is no spread around the mean. If I look at my histogram, it's a single bar. There's nothing else. There is nothing else. Okay, so it makes sense. All the deviation scores should be 0. Great. Why am I doing this? Well, you'll see in a second. If I have scores 2, 3, 4, 5, 6, not very creative, but maybe they were shuffled around, I don't know. The mean is, let's see, 2 is 5, 5 plus 4 is 9, 9 plus 5 is 14, 20, 20 divided by how many there are? 5, it's still 4. It's the same mean, same position. But I have some variety in this case, right? There is a difference between this distribution of scores and the previous one. It's not the same. Previously, I got all the same score, 0 deviation. Yeah, that's correct, correct description. Here, I do have some spread around 4. I got a 2 sometimes. I got a 6 sometimes. I didn't always get the same score. So when we want to reference variability, these shouldn't be the same. But if I do the deviation scores, 2 minus the mean, 3 minus the mean, 4 the actual scores, next score was 5, next score was 6. I'm just picking some easy scores so I can do it by hand, right? I get a deviation of -2, -1. I do get a deviation of 0 there, 1 and 2. So now the sum of all the deviation scores. -2, -3, 0, still -3, -2, 2. So if I add them all up, I get a 0. Still, because some of these deviation scores will be negative when scores sit to the left of the mean. Some of the deviation scores will be positive when scores sit to the right of the mean, and they could be so balanced that the deviation score cancel each other. Fortunately. So the deviation score on its own is not enough, but I'm getting close. I'm in the right direction. To avoid this positive negative cancellation, I do like the deviation scores, but to avoid this calculation, I'm going to square the deviation scores. Deviation. Like there's an I there. I'm going to square it. So I'll then call it the sum of squares, SS, which will be the sum, that's my sigma, of the deviation scores squared. Because if I take any number, negative or positive, and I square it, it'll be positive. So now anything that doesn't sit directly on the mean will contribute to the sum of squares, and no cancellation is going to happen. I really only had two options here. I could make an absolute value, turning everything positive, or I can square it. Absolute values, if you know what that is, uh, it's very clumsy to work with in future calculations. So it's not ideal. Squaring it turns out to be more than sufficient because I'm simply looking for a number to compare between distributions. The first one, the sum of the squares, will still be 0, as it should be because there is no deviation. There's no spread away from the mean. Second one, the sum of the squares won't be 0 because there is some spread, and each of these scores away from 4 contributes to the sum of the squares. And then to complete this, do I have space? Yes. To complete this, we are going to have our actual measure of variability. It's not quite the sum of the squares because if I have more of these scores, each one is going to contribute. I'm just trying to explain how they're spread around the mean. The fact that there are more of them, the spread could be very similar. So I kind of have to average this out a little bit so that it's relative to the number of scores. More scores uh, with the same kind of distribution, same kind of spread, shouldn't have a significantly bigger measure result. So the first one, which is called the variance, is simply going to be average of the sum of the squares. So we can name this in many ways. For reasons that we'll show in a second, variance is going to be represented by SD squared. Now, you could call it just VAR, and I guess some books do, but say VAR for variance. It's going to be the sum of the squares of the deviations over how many scores there are. Now, if you know a little bit more, I'm just gonna, while I'm talking, fix my sigma. It's not very pretty. If you know a little bit more, that's terrible sigma. Maybe I shouldn't multitask. I'm going to leave that. Uh, in later situations, we're going to change this to an n minus 1 for fancy reasons. Right now, conceptually, uh, we're just going to have some numbers, and the variance for those numbers will use an n. So don't worry about this too much. This is actually going to be our next formula. Formula 2.2. You see it over there with a little description. The variance is the sum of the square deviations of the scores from the mean divided by the number of scores. Good. So I'll just highlight here. This is formula 2. Why the number 2? Oh, because it's, I think, in chapter 2 of that book. Right. This is the second formula in our list. So I want to understand what all these means, what all these symbols represent. This is just the name for the variance. I look at my deviation scores. I square it to avoid calculation. To avoid cancellation. I add them all up in my calculation, average them out across how many scores there are. Let's see, we've already done this slide. I think we're one page. Yes, steps for calculating the variance. Subtract the mean from each score. That's my deviation scores. Square them all. Add up all those deviation scores squared, and then divide by how many there are. This is the short form, sum of the squares over n, the more detailed form that you see in your formula sheet. Okay. See that actually done. We have a live in country example, a questionnaire that people were asked, would you prefer to live out in the country with not too many people around? And they picked which one applies to them, and we got a bunch of scores. The mean, we know how to do that now, 3.65. That tells me roughly it sits over here. So slightly more people said no than said yes. Or whatever this rating, 1 to 7 mean. Okay, so that gives me an indication of position. Great. So now let's look at, for each of them, the score itself minus the mean gets me my deviation. Then I square that, and then I add them up to get the sum of the squares over here. You see very quickly by hand, this is already potentially quite tedious to do. Then we calculate the variance as the sum of the squares divided by how many scores there are. We get 3.16. Now, don't try and relate this 3.16 with the mean 3.65. No, completely different things. Trying to say very different things. Now, on its own, the variance number doesn't mean that much. It's hard to interpret just on its own, and not really the point. The point is really when I compare it to another distribution with a similar mean, similar setting, similar maybe scale, but when the variances are different, it tells me that even though the means might be the same, it gives me a comparative indication of how the scores are spread around it, with one variance perhaps being bigger than another. That's one issue, to not look at the variance on its own, but more for comparison purposes. Ooh, I can squeeze it in. There's one issue though. Not there. Issue. that we shouldn't overthink too much, but it is an issue, that the units of the variance, because I'm squaring here, it's the square of the unit of the variable itself. So that makes it really difficult. If I'm measuring people's heights, I'm working maybe in inches or feet, whatever the unit is, centimeters, I don't care. Whatever that unit is, the variance doesn't have the same unit, which makes it even more difficult to interpret effectively. So the variance has unit, whatever the original score unit is, squared, because I squared over here. So what we're going to do is we're going to take the variance and simply square root that, and then we'll have the same unit, and we'll call that the standard deviation, SD. And it's simply going to be the variance square root, which is why we call the variance SD squared, because that is the relationship between the standard deviation and the variance. The standard deviation is the square root of the variance, or the variance is the square of the standard deviation. Now this guy has the same units as x. And though it's not quite as easy to compare a single standard deviation measure, we can see it informally as the average amount of scores. Now, how should I see it? It's how should I interpret this in a sort of intuitive way? The best description, the best interpretation I have for the standard deviation is simply that it's an indication of how scores are spread around the mean, just like the variance is. But we'll soon find out that the standard deviation having the same units of x as x is just much more, it's easier to use in a future calculation. It's clumsy and confusing when the measure of variability doesn't have the same units as the mean and the scores itself. But on its own, it's still a little difficult to just interpret, oh, if the standard deviation is 1, that means blah. No, it's really in combination with everything else that the interpretation of the standard deviation is going to become clear, especially when I compare two distributions with uh, or between two distributions. Where's that slide now? Not this one. This one. So here, for example, of course, we'd have to actually calculate it. Here, the standard deviations. This one might be a fairly small standard deviation because my uh, deviation scores aren't big. So even if I square them, they're not big. The square root getting me to the standard deviation just sort of normalizes things back to the same unit. If the variance is big, the standard deviation is going to be big too. So the one is directly related to the other one. For these two, it's hard to say. This one might actually have a larger standard deviation, but let's just compare these two, if nothing else. When I compare them, even though the means are the same, I now have a number without looking at the histogram and trying to visually assess. I guess this one is definitely spread differently. Is it spread around the mean more? Drastically spread around the mean than this? Visually, I don't know, especially when the difference is slight. But by having a number to compare, on its own, that number might not be as easy to interpret right now. It'll become easier. But when I use it for comparison purposes, then I can say, well, this has a larger standard deviation, so I am more likely to see scores that differ from the mean. If the standard deviation is small, then I don't expect to get scores that differ from the mean a lot. It, of course, will differ, but not a lot. It'll hover around the mean most of the time. If I have a larger standard deviation, then I can get scores quite often that are much lower than the mean or much higher than the mean. I get a much wider spread with a larger standard deviation. Small standard deviation, I get a much tighter distribution around the mean. There's still some spread, but much, much less. So the standard deviation is the perfect measure for this spread around the mean. To give me an indication whether I can see a distribution or not, if you give me the standard deviation, especially two different ones, it gives me an indication of what to expect. Well, I expect a lot of variety in my scores with a large standard deviation. Or, ooh, the standard deviation is small, I'm going to get something very close to the mean almost all the time. Now, how small is small and how large is large? Well, that is an issue for the upcoming topics. Let me just see if I've covered all the slides. We've done that. We can go back to our live-in country example, where calculating the standard deviation is just a very small step from the variance, because the standard deviation is just a more convenient version of the variance. They are saying the exact same thing in terms of what they're measuring. So I just take the square root, and the standard deviation is 1.78. What does that mean? I can't really say much at this stage, but we will. Let's go back to our horn honking example, which you hopefully remember. I can do for both of these. Calculate the squared deviation, sum of the squared, sum of the squares here and here. Only starts to make sense when I actually sort of average it and calculate the variance, and then the standard deviation there and there. And you see that with the existence of this outlier, the standard deviation and variance, they are sensitive to outliers. But that's not a bad thing anymore. They should be sensitive to outliers because they are trying to convey information about how wildly things can vary in the scores that I can get. So if I get an outlier, that tells me I can get scores that vary quite a bit. And that should be reflected in the standard deviation. If I now have two that I can compare with each other, the second one, the one on the right here, should be bigger. Actually, it's much bigger because in its set of scores, it got things that differ quite a bit from the mean. It needs to reflect that is possible as far as it's concerned. Whereas as far as the left one is concerned, yes, things are spread around, but packed quite tightly around the mean. It didn't get anything extreme to indicate that a wide spread is possible. So we have, to sum up, the measure of center, focus on the mean, be aware of the others. Mean is going to be our main player, but that's only half the picture. Variability, having a number to represent how the scores are spread around the mean. Is it spread widely? I can get all kinds of stuff, or is it packed quite tightly and I can't really get a lot of variation? Variance, standard deviation. That is my go-to measure. All right, we are at the end. What we now have to do is actually solidifying this concept, this understanding, by doing some calculations by hand. And we'll quickly see that if we have a lot of scores to work with, it can get quite tedious, but it's still an important step that I don't want to skip. And then we'll systematically make that easier as we transition from a hand calculation to actual software options. But that will be for next time. See you then.